Okay, to matters at hand. It's my pleasure to introduce to you Terry Engelder. Many of you, I suspect, know Terry. He's currently a professor at Penn State University, and he also earned his undergraduate degree there several years back. Some of you in the audience will recognize Terry as a graduate student in Yale's Department of Geology and Geophysics department, where he was here from 1968 to 1970 before moving to Texas A&M to finish his PhD. I could read you a long list of Terry's academic credentials, but I wanted to do something a little more interesting than that and get some personal information. And so when you're after personal information, what do? You go to Google. So I Googled Terry, all right, and I found out that Terry's been a prime focus of media attention since 2007 for his work that he's done in the Marcellus Shale. This attention culminated with Washington Post Foreign Policy magazine recognizing Terry as one of the top 100 global thinkers. And this is pretty rarefied air. Other people on this list include President Obama,
high or low,
Secretary of State Clinton, Defense Secretary Gates, and also Britain's Prime Minister David Cameron. So this recognition in turn led to an invitation for Terry to attend the Obama administration state luncheon, where it was discovered, tongue-in-cheek, that Terry, on this top 100 list, actually outranks Prime Minister David Cameron. So with that, I'm going to turn it over to Terry.
Well, all right. Thank you very much, Jim. Now, is this microphone on? And we're all set, I guess. The one thing I didn't discover up here was the clicker, how I advance this. All right, now how is that?
The microphone is on.
This microphone is on. Maybe what you want to do is turn that guy off. How's that sound?
I have to have the video guy up here to do that. I don't know how to turn this off. I can get it out of your way, perhaps.
I think you just did. Raise the microphone on his lapel.
All right, this is the one that's the room mic here. And we'll bring this higher. How's that?
Sounds good here.
How's that sound? Okay.
Terry, and to advance, you have to do it.
Oh, all right, the old-fashioned way. I wanted one of these things, so that means I have to get out my wand here and do this. All right. Thank you very much, Jim. It's a pleasure being back here, and in fact, I have a lot of very warm memories of Yale during the 2-year period of time that I was there. And a couple of the faculty still remember me, particularly Carl and Brian. What I want to do is describe one memory that neither of these people were aware of, which is that Yale's premier distance runner, you guys might remember that Frank Shorter won the gold medal in the marathon in Munich in 1972. What you didn't know was that I was a distance runner as well, and that in the IC4A championship of March of 1967, I ran against Frank. Here I am right here from Penn State. There's Frank right there. And this is a relatively famous photograph back at Penn State. Now, when Jim introduced me, he made the point that the media first focused attention on me based on the calculations that I did for the Marcellus in 2007. Ironically, it turns out that Frank Shorter was the first to recognize me. Here he's dated it. You can't see the date right here, but it's dated December 13th, 2007. Frank, I think, did this because he recognized he's been the subject of media attention for a long time. I've known him for a length of time. In fact, one of the interesting things is that when I came here as a graduate student, he was a year younger than me. That was his senior year. when he was training, and it turns out that there was no one on the Yale track team that could go through a full workout with him, so I spent weekends, for example, going on 20-mile runs with him. And that spring, he became the 10,000-meter champ, NCAA 10,000-meter champ. And so rather than doing geology on weekends, I was doing this. And this is something that you guys did not know. Okay, so that media attention, again, started in 2007. It was about October 2007. Frank's signature on that particular race from Madison Square Garden was sent to me 2 months later. This, it turns out, is the 294th talk that I've given in that period of time. I think more significantly, in that period of time, I'd been approached by 424 different reporters. And you might ask, how many reporters has the president been approached by? Probably quite a bit less than that, because he's not as busy as I am. The cumulative attendance right here is above 20,000. Now, how do I know that? What I do is I know that because it's all recorded in a series of notebooks like this that I've already had Brian take. But if you could pass that around, you'll find right here on page 98, some people have signed it. Actually, why don't we go from the left side, pass it back, get it through the audience. Let Kathy sign it first, Brian. So,
when you speak, if you could speak away from the podium.
So this is picked up. Okay, let me get away from that then. And this is okay with you back there? All righty.
Perfect.
There you go. That'll take care of it. Typical modern talk. It just takes a while with the AV and all of this other fancy stuff. Back when I was a student with Brian, you just got up with a piece of chalk and started talking, and it all worked back then. Okay, so now what is this fracking business all about? And it's important probably to draw an analog with the literature. In this case, the literature that I draw upon are two relatively famous books concerning the collapse of civilization. And on the left is Tainter's book, written in the late 1980s. And his hypothesis was that energy capture would lead to, or did lead to, the collapse of civilizations. And this is a counterpointed view written by Jared Diamond. Most of you remember that, written about 10 years later, and his point of view is, no, it was environmental mismanagement that led to the collapse of many civilizations. So in the fracking debate that we're talking about right now, what I want you to do is keep in mind these two particular different points of view concerning the collapse of civilization. Keep that as an analog. So what we find is that in the debate that I've had in the literature, this is a fairly well-known paper that was written about a year ago in Nature. It's a point-counterpoint. Should fracking stop? And one view was, yes, it's too risky, and the other view is, no, it's too valuable. Both views, however, and it's very important to appreciate this, both views are fraught with moral ambiguity. And you've got to keep this in mind as well when we talk about the fracking debate. So the two sides actually are represented by Tony and Graffia, who argued, yes, this is too risky, it should stop immediately. I represent the other side right here. No, it's too valuable. You recognize a notebook being passed around. This picture actually comes from a talk that I gave in Czech Republic about a month ago. Who has the notebook right now? And if you take the yellow sticky and open up to that page, there are the signatures of the people that signed this notebook right off of this talk. Tony, on the other hand, rather than passing around notebooks, nuzzles up the famous people. You'll recognize Yoko Ono right here and other famous anti-frackers. So this is the view, and of course, you might ask in this analog, who's represented by this? Well, Tony represents the point of Jared Diamond, which is that the environment is at risk, and that is entirely true. I took the point of view that, no, it's energy capture that really is the most immediate. Now, one of the other things I want to make very clear is that in 2007, long before Frank Shorter sent me that picture signed by him, I had to sit down and actually go through the process of saying, this is really going to affect such things as the amount of CO2 released in the atmosphere. Do we really want to do this? This is also going to be a tremendous help to such things as American energy security. Do we really want to do this? This is a balance between two choices. There's no right and there's no wrong, but I don't think any of us in 2007 fully anticipated the extent to which this would become politicized, and it is now a public debate. Ironically, the reason I like to show Tony is Tony and I wrote a paper together about 15 years ago on hydraulic fracturing. And so I've known Tony for a long period of time, and one of the things I have to say is that there is no more passionate, better debater in terms of defending his point of view than Tony is. This guy is brilliant in terms of his speaking style and his ability to engage an audience, and a brilliant scientist also, so a very interesting partner in this particular business. Okay, now, global thinking, how does this play out? Here's an interview that I gave last May in the Czech Republic, and I was interviewed by this science reporter for the large daily newspaper Nice in the Czech Republic, and I was quoted as saying, some Europeans fear the propaganda in Josh Fox's movie Gasland more than the hand of Vladimir Putin on the valve that supplies natural gas to Central Europe. Now, ironically, just the day before yesterday, a reporter for the large French weekly magazine called up, and I tried to get him to quote this particular quote, but replace the word Vladimir Putin with the word President of France, because in fact the French have voted to ban hydraulic fracking, and for better or for worse. Now, the point that needs to be made is that the French succeeded in the 1970s in developing electrical generation capacity using nuclear power plants. There's no other country in the world that has the same luxury. So that in fact the French president can actually ban fracking without really affecting the electricity supply of his nation. Here's the actual publication. Of course, it was in Czech. And within 48 hours, 42 people commented on that, normalized to the American population, that's 1,260 people. This is an exciting thing for people to write in about in this new media. All right, now the debate continues, and it continues to the point where Hollywood is going to release a movie this coming December 28th entitled Promised Land. This is a Matt Damon movie, and in this movie, what you'll see are a series of dead cows that have sort of dropped over in northeastern Pennsylvania. This is pure fiction. Now, of course, there was one case in Louisiana where barbed wire around an open frac tank was broken, and some cows decided to drink of that stuff and did suffer a tummy ache as the result of this. So the point, though, more importantly, is that this particular movie is funded by Middle Eastern banks. Now, why would Middle Eastern banks fund a Matt Damon movie? And it's very simple, which is that there are a couple countries, Qatar and the United Arab Emirates, whose total economy is a gas-based economy, so that when gas from gas fields like the Marcellus depress the global price of natural gas, the entire economy is affected. And so these guys are going to push back as hard as they can against the North American gas play. And one of the ways you push it back is you put into the media a lot of fiction. In fact, this is a little bit like Gasland. Now, on the other side of things, you'll notice right here, facts funded by by an American business. So this is really a global competition. The international businesses pushing back, the American businesses funding this. Now, guess how long ago this happened, where Larry Cathles, Terry Engelder, and Fred Baldessari were standing in this field. That picture was taken less than 24 hours ago. In fact, as on my way over here, this film crew got us, and they approached us for a couple of reasons, not the least of which is they said, we've got to prepare, we, meaning the American businesses, have got to prepare to push back against this movie, which is going to capture the public. and in a way that sort of lets this get out of control. Now, a little bit of an explanation here. Fred Baldessari is the Pennsylvania DEP geochemist that was originally assigned to look at methane migration in the area of Dimock and to look at water chemistry in the area of Dimock. It was Fred who was basically crying out in the wilderness saying there is no evidence of frac fluid in the Dimock area polluting groundwater. And people kept saying, no, you're not getting this right and whatnot. And it was only recently when the DEP for a second time said, EPA, the federal EPA for a second time said, no, this water hasn't been polluted. Now, the interesting thing is that when EPA came out with that, the end of the script for this movie had to be rewritten because, of course, it was going to be a conclusion in which people were poisoned and people were affected one way or the other. So the movie got changed. Larry Cathles is an expert on two-phase flow through rock and also has been stating for a long time that in fact, it's a consequence of two-phase flow that assures that American groundwater will be protected. Now, I'm going to talk about my role right in here as well. But in the meantime, you see this right here? This, again, is that ever-present notebook that you're passing around. These guys also signed it, and if you want to turn to the previous page, you can look at the signatures from these guys as well. So, at any rate, we move forward then. Why is it that natural gas has really had an impact on North America? This is the New England power grid and how it's evolved over the last 10 years. And one of the spectacular impacts of natural gas, particularly from the Marcellus, on New England electrical power generation is that coal-fired power plants supplied 16% of all electricity in New England as little as 10 years ago. And right now, that's been reduced to 6%. And I'm sure that some of you have heard in the last 6 months that EPA has announced that the amount of CO2 emissions from American industry is lower than it has been in a long time, mainly as a consequence of natural gas right here pushing back on the coal industry. This is spectacular. Question?
Can I ask a question? Is that corrected for the downturn in the economy? Because there was a natural drop during the financial crisis.
No, this is normalized. This is a percentage.
Okay.
This is percentage normalized. I think moving into the future is a fairly important thing to do with this particular chart as well, because we have a lot of people who say, well, that money that's being spent developing natural gas should be spent developing renewables, wind and solar. So we're going to look into the future of New England. And one of the things you see is that the future capacity of New England does include a large component of wind right in here like this. But you'll notice that for every megawatt of wind-generated electricity, there will be a megawatt of natural gas-generated electricity. And I've made it very clear, which is that wind is not continuous. You have to back it up. And in fact, is the carrying capacity, the average carrying capacity for wind in the eastern part of the United States is somewhere on the order of 7%, which basically means it has to be completely backed up. And that's what this particular projection looks at right here for New England's future. Yeah, Jay?
How far in the future is that
Oh,
projection for?
I'm not sure what this is in terms of a period ahead. You'd have to go back to NECA to find that out. But the point right here is that in terms of the renewables, they're great, but somehow or another energy has to be stored, and we don't have the battery capacity or the storage capacity to take up anything that is left open in terms of generative capacity when things like the wind doesn't blow. All right, so that's the good news. And in fact I would say that looking at that, if I had known that this would be the outcome back in 2007 when I originally went through this period of questioning about whether or not talking about the value of natural gas to North America relative to its impact on the environment, this is a really positive outcome that I couldn't have imagined. All right, now, there is public concern in Pennsylvania that the Marcellus frac fluid can mix with groundwater, thereby causing an outbreak of health-related problems among those who drink water. We all would agree with that. And so the question is that true? We need to pass that on to the center section. Now, in fact, this has been reinforced by the recent literature. This is a publication in the National Academy of Sciences, and the title of this particular article is Geochemical Evidence for Possible, and I emphasize right here, possible natural migration of Marcellus formation brine to shallow aquifers. This is written by a series of authors from Duke. All right, so that's the title of this paper, and you all know what the word possible means. The problem with this, of course, is moving forward into the popular literature, and I would suggest that this particular magazine, this is the December issue of National Geographic. This arrived in my house about 2 weeks ago. And if we look into the December issue of National Geographic, there is an article entitled Fracking for Methane. By golly, let's see what they have to say. And one of the things we find here is that the title of the story is Good Gas, Bad Gas. I really love this picture, though, which is a termite. Termites actually generate a lot of methane right there. Termite captured in amber with methane seeping out its tail end. I don't know how he did that when he got captured in amber, but that's a beautiful picture. There are a lot of ways that methane gets into the atmosphere. And you all understand, of course, that methane is a global forcer, and that some of the debate over fracking involves the amount of methane that might leak into the atmosphere as a result of drilling. And so this is the statement, though, in National Geographic that caught my attention. Now remember that we have this possible geochemical evidence for possible migration. Now that geochemical evidence is based on an incomplete data set. No consideration was given to the geological reality in that interpretation. It is an interpretation, but suddenly that interpretation in the popular media right here gets turned into a fact. Duke scientists have recently reported evidence that fluids have migrated upward from the Marcellus through natural fractures and into groundwater, if you read that paper. So here's an interpretation that all of us understand now in the public domain is a fact, so that in the review process there was some pushback against this particular paper from Duke because of the fear that this is immediately going to be seized upon by the public, misunderstood, and turned into a fact. And once the public turns a piece of science into a fact, it is awfully hard to reverse. Now, the reason that I say that this was based on an incomplete data set is found in any type of log that is produced from the Marcellus. So here's an electrical log. It's produced by a Schlumberger. This is a gamma ray log right in here. This is a lithology log. You can see the underlying Onondaga limestone right here. And admittedly, this is a very, very complex diagram. So what I'm going to do is I'm going to just draw your attention to this portion of the log right in here, bearing in mind that most of this is Marcellus up through here. So I'm going to show you Marcellus right here, and we'll look at this in detail because this is the crux of the geological argument used to demonstrate that the evidence for migration of fluid from the Marcellus into groundwater is probably not the correct interpretation. And so let's spend some time looking at this. First of all, let's understand the various plots right in here. First of all, the porosity, which is shown right in here, from 0 to 40%. This is actually intense right in here from 0 to 1. So 0 porosity is here, 40% porosity, the rock is right there. And this dashed line represents porosity. And so what we see are 4 components to that porosity. One of the components is clay-bound water. And the clay-bound water, in effect, is this area right in here like this. So that in a Schlumberger eland log, which is what this is, Porosity doesn't mean open space in rocks. It really means that stuff that's filled by hydrogen. This is largely based on a log that we call a neutron porosity log. So some of it is clay-bound water. Some of the porosity is actually bound water. You'll notice they're called the same, except that here bound water means surface-bound water. Surface-bound water basically is the stuff that when you pour a glass of water, the inside of that glass is still wet after all the water has been poured out of it. That's surface-bound water, and that shows up as gray right here. And you can see on a scale that is a porosity scale that goes from 0 to 40%. There's just very little bound water right in here like this. Now, the other two things that are found in this porosity include a little bit of free water. There's a little bit of free water right here and a little bit of free water right here, but no free water anywhere in the major portion of the Marcellus except for one spot right in here like this. Now remember this Duke paper, geochemical evidence for migration from the Marcellus. That migration has to be in the form of free water moving out of the Marcellus. The Marcellus is virtually dry in terms of free water that can actually migrate outward. One other component in the porosity of the Marcellus is natural gas. This is methane, and what you can see in this particular portion of the Marcellus is that as much as 16% of the Marcellus is composed of natural gas right in here. This is why the Marcellus is so rich. You have this unit that's on the order of, I don't have the scale right in here, but this is 100 feet. This is a 100-foot tank that encompasses somewhere on the order of 31,000 square miles, some number like that. I mean, it's a huge number of square miles. 100 feet thick, 10% of it is natural gas. And it is obtaining that natural gas that then allows America to move forward in terms of gas security for a long period of time. Yes, another question.
I didn't read the Vengosh paper, so I'm just curious. How did they conduct their study? Can you
Yes, I hadn't planned on it, but just very shortly, Vengosh sampled flowback, and I'm going to talk about flowback in a few minutes. So he did not sample natural fluid. He sampled what was the result of the interaction of water pumped down and water and chemistry that basically is diffusing out. Now, Sue Brantley, some of you know Sue, is a really good Penn State geochemistry, and Sue Brantley and I are putting together a paper right now that proposes a model by which you can salinate flowback water based on the chemistry of what is left when you drive off initial sea bottom water. Now, remember that when the Marcellus was deposited, it's sitting on the sea bottom as an ooze that probably has an 80% porosity filled with sea water. That has to be driven off completely by the process, first of all, of compaction, and then the maturation process. And this rock gets dried out during the maturation process, which means you expel an unbelievable amount of hydrocarbons from this rock, leaving only a little bit of gas behind. And during that process, in effect, you turn this into a dry rock during that period of time. All right, so what Vengosh did was measured the chemistry of the flowback, not natural water, and observed that the strontium isotope ratio of the flowback water resembled the strontium isotope ratio of water in water wells. And therefore, one must conclude that this is coming from the Marcellus. Now, the flaw in this, of course, is that there are so many other formations that are sitting below the Marcellus, including the Oriskany sandstone and the Medina sandstone that have a huge porosity, a huge amount presently of oil field brine, natural brine in the rock, and there's no doubt that and they've measured that chemistry as well. That chemistry matches what's in groundwater, and at least in my mind, it is far more likely, if we use Occam's razor, it's far more likely that the rock in the subsurface that contains a huge amount of free water can be the source of this stuff in groundwater, not the Marcellus, which is now virtually dry. So this is the geological argument right in here. It is that this is a dry rock. Now, the Marcellus does contain a lot of fractures, and people have argued, well, it's the fractures that allow water to drain out of the Marcellus. Let me point out that this natural gas in the Marcellus is overpressured. Now, what that means is it has a fluid pressure that exceeds the hydrostatic gradient of any water that's on top, so that if the Marcellus were leaking water naturally, water has a much higher viscosity than natural gas. And as all of you know, if a fluid is going to leak out of a porous media, it is the low viscosity component of that porous media that's going to leak long before the high viscosity component. The point is that all of this natural gas, even if it leaked at the rate of 1/250 millionth a year, would all be gone now. This maturation occurred somewhere between 270 million years ago and 250 million years ago. This rock has been sealed as a result of capillary forces for that period of time, 250 million years. And so over that period, if it didn't leak this gas, a very low viscosity fluid, it certainly did not leak high viscosity water out. All that water was driven out a long, long time ago. Now, to be honest about the Duke paper, they did say, we don't understand the time scale of this. All we did was we observe a chemistry in flowback that matches a chemistry in water. Therefore, we conclude that this water that is sampled in the ground right now, groundwater, drinking water, is somehow or another related to the Marcellus. And there are so many other geological explanations for the chemistry of groundwater that does not require calling upon anything escaping that section right there.
But Terry, didn't they
Yes.
argue also that there was a lot of massive drilling all around the place for exploration purposes, and essentially making Swiss cheese out of the sediments, and therefore any chance of any movement of water would bring some of the strontium isotope imprint of the Marcellus up to the surface. They did invoke that as a possibility.
Well, the problem, though, Carl, with a lot of that is that the massive drilling in the Appalachian Basin is largely shallow oil sands like the Bradford and the Elk and whatnot. And so the Marcellus is less Swiss cheese than the other formations. That coupled...
But their argument is that some.
Well, you got to be a little careful, right, because the wells that drill through the Marcellus are drilled on anticlinal structures for Oriskany gas sand, which is now gas storage fields. And what these guys were doing, the Oriskany fields are either in central or western Pennsylvania, and what these guys were doing was sampling groundwater in eastern Pennsylvania, where there's been virtually no drilling. And so even when they mixed the data from the Medina, they had strontium data from the Medina, which sits below the Marcellus, and the Clinton sands, as well as data above from the Bradford and the Elk sands. That was all western Pennsylvania stuff. So they were taking two geochemical samples from two different regions and mixing it together. Yeah, question?
So tell me where I'm going wrong here. It seems like another way to think about it is, yes, it's been holding the gas and the free water for 250 to 370 million years, but then when it gets hydrofractured, and then you can extract the gas, couldn't that also then liberate and allow it to be permeable to free water?
No. The reason for that largely is that when the rock is hydraulically fractured and the well is produced, the pressure gradient, which basically is the component of Darcy's law that really matters, the pressure gradient is an inward gradient towards the well bore. And so it's that gradient that actually drives everything up the well bore, not outward from the Marcellus through this capillary seal and upward. And even if some of the hydraulic fractures break their way through the top of the Marcellus capillary seal, once flowback occurs, it's all inward toward the well bore and then up the well. So that in a sense, further assures that this stuff doesn't get out of the Marcellus, but rather flows up the wellbore. And the important thing about flowing up the wellbore is that it then can be managed by proper engineering, and which means putting flowback tanks, making sure there are no surface spills, because a lot of the people that have looked at that said the real danger is not in the subsurface flowing by natural pathways back, but rather the management of this water at the surface as it comes back, either the disposal of it or the retreating of that water. And that is something that can be supervised by engineers so that with proper practice, that no longer becomes a problem. Yeah, go ahead. Yeah, please.
You made these comments, and it will be published apparently soon, about their paper, right? You're publishing the comments.
Yeah, what happened, Carl, was that the Academy asked me to write a commentary, but they said you can't criticize the Duke paper. But what's the point of writing a commentary if I can't?
I thought there was a response mode. There was no commentary and response with them.
No, they rejected my commentary because I wanted to publish this. And
I think what they asked that you do is submit a commentary on the article that they could respond to. That wasn't done.
Actually, the way this is playing out is I wrote a letter that was accepted, and I'm not sure whether they wrote a comment on the letter or not.
They usually do.
Do they? Yeah, all right. Then that's actually in the works. My letter has been accepted, and whatever they wrote back has been accepted. Yeah, it hasn't been published yet, but it's been accepted. But the problem with that was reduced to 500 words, and I couldn't include that particular figure in the whole thing. And for the rest of the audience, science is so much fun because, of course, it is open to debate in the peer review literature, and obviously Carl has revealed himself. I've revealed myself. I was the minority reviewer on this paper that was four reviewers, I think, wasn't it, Carl?
Yeah. Remember, I asked you to be a reviewer.
Yeah. And Carl was the, what do you call that? The handling editor and whatnot. And of course, poor Carl is in I shouldn't say poor. Carl was like any editor, in a situation where you have a minority opinion and a majority opinion, and you just, as an editor, I've done this with JGR, GSA, tectonophysics. It's just it's a situation where you can't win, and of course the.
My only comment was there a response to your thing, and you don't know that?
Yeah, I don't know it. I haven't seen it. They're allowed to respond. It's sort of like these typical comments. This will be published elsewhere, though. We'll get this out into the open. Yeah, I guess that Carl, my one response, of course, is that the Proceedings of the National Academy of Sciences publication is fine if it's not going to be seized by the public media and then misinterpreted, which these guys really did. I mean, they turned it into a fact when there are other interpretations that I think are far more logical. And again, I have to emphasize that if all you have is a geochemical data set and you want to interpret it, then you arrive at what I think is a fairly logical conclusion, which is fine. But these guys failed to incorporate the larger data set, which includes geology and geophysics as well. And that's where we got into a little bit of a tiff, or whatever one wants to call that. And one of the things I want to make clear is this is not a case of sour grapes on my part, because the truth will eventually emerge on all of this. But it is a lot of fun, and it's sort of a pleasure talking about this afterwards, because, of course, the public in general doesn't understand quite how this process works and is willing to seize on pieces of science that seem to satisfy their particular biases. And that's sort of how the Marcellus and gas shale in general has gone on in terms of the polarization of all of this. Okay, I want to make another point right here, which is that when water is put down into the Marcellus, some of it flows back, and the flowback curve in time. Now bear in mind that this is a cartoon. The flowback curve in time for water looks like this, and for gas looks like this. And water, of course, comes out of a rock that is water wet, and basically you can't get gas through pore throats that are water wet. And so that's an important piece of information to have. In terms of terminology, notice that there's a point in time in which gas production starts. This is known as production water that's produced right in here. First water that comes back is called flowback water, and it's a massive amount of water. But when the flowback water comes out, you'll notice gas production is relatively low and then gradually increases. Now, in terms of the Hallworth paper that came out, and in fact is even in that Nature debate where I said, yes, this is too valuable, and they said, no, it's too risky in terms of the environment. What those guys are concerned about is industry capturing this portion of the natural gas that comes back with flowback. And there still is some question about the extent to which industry is doing a good job of capturing this. And a lot of people argue that most of this is captured. It's not escaping. And Hallworth's worst case scenario is that this methane right here is escaping. Obviously, once the well is online and it's producing back in here, why engineering assures that the gas can be sealed. One of the things I should point out is that in this article, Drew Schindel, who works with NASA and is an expert on global climate, points out that capturing methane produced in this manner is not the big worry in terms of global climate change. It can be engineered to make sure that a lot of the seals are fixed. In fact, very early on, Richard Alley, who's a colleague of mine, also said, when you talk about this, just point out that industry can find the leaks and fix them. And that this is not quite as big a concern as has been made out in the literature. All right. Yeah, go ahead.
Clarification. I presume that the waters are always saturated with respect to methane, so you're always dealing with two-phase flow, is that right?
Yes, that's correct. In fact, thank you for bringing that up, because I do want to trip back right in here. Another point on this graph that I didn't emphasize is the water saturation or gas saturation right in here. This curve right in here, which is water saturation is in blue right in here. And the curve you'll see goes from 1 to -1, which means that just the left side of this really matters. And in terms of water saturation in the Marcellus, you can see water saturation is less than 10%. Here's a little more water right here where we have free water. And this is gas saturation right here, up above 90% through here. And that's what makes a really good gas shale. In fact, as we're learning from places like Poland, that if you have a water saturation that even approaches 50%, like this right here, that blocks flow of Marcellus out of the formation. So this water saturation right here, very low water saturation, of course, is what makes gas shale possible, and the reason that we call this a dry rock, it's dry relative to free water.
I'm embarrassed that my own company has -1 for saturation.
Well, I mean, you know, what can you do?
Move to the left, basically.
Yeah, I don't know why they did that, but it's for plotting convenience. All right, now one of the things that I do in a talk is I present too much information invariably, and I run out of time. I do want to make one more point that it becomes reasonably important in all of this. The question is, this is a side point, incidentally, to the National Geographic article right in here like this. And again, the popular media captures things that are just not true. In this instance, it's pointed out that DOE made a prediction for unproven reserves in 2011, and in 2012 this was cut by 40%. Now I can't tell you the number of times I've had anti-drillers shove this back in my face. You were unconscionably high in your prediction. Look at what the USGS has done and whatnot. And the important point is that the way that gas shale reserves are calculated really depends on how they're calculated. So the National Geographic makes the DOE look like fools. natural gas in the Appalachian Basin has been produced for 40 years or more. There has been an experience of 40 years looking at decline curves, horizontal production from the Barnett in Texas. There have been 10 years worth of decline curves. It is extraordinarily disingenuous then to say that suddenly, somewhere in 2011, the DOE, through EIA, the Energy Information Agency, suddenly discovers that, oh my gosh, these wells are declining more rapidly than we thought. You know, it just, that's as far as I can tell, an insult to that particular agency. And, you know, again, a misrepresentation of what's going on right in here. All right, now, the water that's put down in the well and the flowback, basically 80% of that water will stay in place forever within the gas shale. And right in here is a table from a number of wells taken more or less at random throughout the Appalachian Marcellus play. And what we can see right here in wells that have been produced for a long period of time, this one is an anomaly, and I think it's an anomaly because often what happens is operators will flow back more than one well into a flowback tank. And the data that is recorded right here is the amount that comes out of the flowback tank, regardless of whether it's one wells or many wells. And on average from this data set right in here, 11% of the injected fluid comes back. And so a lot of people have said over the years, well, what about that other stuff that's down there? Is that not leaking back to the surface? Again, going back to the Duke hypothesis that all the rest of the stuff has somehow or another gotten out of control and away from the geological realm. And what I'm going to do is show you in a little bit of time what two immiscible fluids will do. In this case, water and air. Now, you've all seen these cartoons showing the boundary between these two, and this boundary is held high by surface tension. If this is a fluid in air, or interfacial tension if it's two different fluids. And the data that we have on surface tension and interfacial tension is very clear right in here. Mercury, for example, against air has a surface tension of 480 dynes per centimeter. Obviously, water in air and methane and water and oil shown right in here like this are considerably lower. So the common model for this is shown right in here in the form of a bubble that sits on a surface like this. This convex surface right in here is held in place by surface tension from these molecules. Now here's a concave example of surface tension in a concave manner right here. So we keep track of these two, a convex or a concave surface tension. There's another force that governs fluids, and that force is known as wettability. And basically, it's the tendency of one fluid to spread or adhere to the other fluid. So it's a force of adherence. And in one case, we have water on a water-wet surface, the water will spread out. If water is on an oil-wet surface, it will tend to bead like this. Now, watch this. If we do a series of relatively simple experiments, here's tap water, for example, on Vaseline. Vaseline is water wet. This is the angle of wettability right here. So this is, if this angle is high, water to whatever it's on right in here, that means that we're looking at an oil-wet surface. Notice the volume here, 33 milliliters, and the angle is 105. This is at 0 minutes. Now, to do a series of experiments, one has to account for a number of things, not the least of which is what happens if you add to the volume of that initial bubble. And so I've added to the volume right in here, it's 77, 154, 231, 308. And what happens, of course, is that the weight of gravity causes this bubble to sag so that that interfacial tension angle decreases like this. Now, the other question is what happens with time? And so here is that 77 milliliter, or 33 milliliter bubble here. As time goes by, and you can see the bubble decreases, the reason that that bubble decreases, of course, is evaporation does allow this particular fluid and the components of that to move through the surface of tension and into the atmosphere. We see the same thing over a longer period of time. So here is a bubble of 77 microliters over a period of 217 minutes. And just keep track of that, because now what we're going to do is look at the effect of surface tension and the force of adhesion. When you combine these two, that's called capillary pressure. And capillary pressure is really defined by the height of a column of a liquid right in here. This would be water, for example. That has displaced air that follows a hydrostatic gradient that looks like this. So these are two hydrostatic gradients, and the departure of those two hydrostatic gradients is a measure of capillary pressure. All right, now, capillary pressure does something that is very interesting in a rock itself, which is that it serves as the mechanism for imbibition. So I've taken that previous experiment, which is a capillary tube, turned it on its side, and looked at a pore throat right in here like this. And in this case, this is a rock with grains that are water wet, and we have gas trapped in it. And basically by capillary pressure draws, or the adhesion to these surfaces draws this water column into that pore throat and basically prevents gas from flowing out. And this then is the mechanism of imbibition. It's also the mechanism of capillary seals. This is the physical process that allowed gas to be trapped in the Marcellus for 250 million years. Here's a definition for imbibition, which is a very important statement, which is imbibition is a fluid flow process in which the saturation of the wetting phase increases. All right, keep that in mind, because that has a great deal to do with what I'm about to say, which is that when we start looking at rocks of different permeability, here's sandstone, here's a gas shale right in here. The permeability of a sandstone is on the order of millidarcies, which is reflected by this first 3 decades right in here. Shale has a permeability of nanodarcies right down in here like this. And it's when dealing with rocks of nanodarcy permeability that one then really has to become concerned with two-phase flow. That's why I've colored this in blue, whereas sandstones up here with a fairly high porosity, large pore throats, then single-phase flow can explain what is happening. So what we're going to do is a series of experiments looking at such things as gas-driven hydraulic fractures. These are natural fractures that propagate under gas drive, and the gas recharge by flowback through the wall of this particular fracture allows the fracture to recharge and propagate onward. Now, in my career, if I have to identify one paper that has had an impact on the gas industry, it was the recognition about 20 years ago with a graduate student of mine, Alok Azet, that a lot of these natural fractures, particularly in gas shales, were a consequence of maturation with the production of natural gas. Now remember that maturation process is an endothermic process, and usually when you have an endothermic process, that is a volume increase reaction, and that volume increase reaction leads to high pressure gas that drives these fluids. Now for all intents and purposes, what we're really concerned with here is the motion of gas in and out of the wall of this fracture, or fluids for that matter, through that wall, in the rate at which they move through the wall. So we're going to do a series of imbibition experiments, which is that here is one of those gas-fracked sand joints right in here like this, and I'm going to put a sample of water. I'm going to put 156 microliters of water on that surface and measure the length of time that it takes to imbibe that water. And what you can see is that after 1 minute and 50 seconds, most of that water is gone. This is just like pouring water on a sponge. And it's that speed with which water moves in and out of sand layers that allows for the process of natural hydraulic fracturing above the Marcellus. Here's another formation. Again, we have 154 milliliters. Here's 77 milliliters. You can see that within 17 minutes for this rock right in here, it's slightly less permeable, but the bubble on the surface is gone. Here's a look at a gray shale, and what we see with a gray shale right in here is that 65 minutes have passed before that bubble disappears, so that we have a very low permeability rock right in here. Notice the order of magnitude. There's 4 to 5 orders of magnitude difference in permeability between these sandstones that I've shown you and this shale, and yet the shale is able to take up this water in somewhere on the order of 60 minutes. Now bear in mind that those experiments with a water-wet surface, Vaseline, those bubbles consumed about 200 plus minutes in order to completely disappear by evaporation. So there is evaporation going on here, but part of it is imbibed. All right, now the punchline right here is that I acquired some samples, cuttings from the Marcellus, recovered in mid-November from the Bushwick number 1 well, right about here, for example, in this horizontal well. This is several thousand feet below the surface right here, and as they were drilling the well, they were back in here. All of you have seen pictures of the process of drilling a horizontal well on the Marcellus down below the surface right in here. Those cuttings, then, very simple experiment. Cuttings from the Marcellus. These are the cuttings that were in the ground less than 2 weeks ago. And I just put this on here for a relative scale, just so that you can see what's going on. Now watch this. This is really slick. We have here a gas shale that has a permeability that is less than 200 nanodarcies. And yet in 85 minutes, this rock of less than 200 nanodarcies is consumed at least part of that bubble. Now bear in mind that part of it is gone because of evaporation. But what is really interesting in all of this, and let's see, does this show up? Can you see? Yeah, all right. What really is interesting in this is looking at this particular slide. That area right in there you want to look at, because you can see after 1 minute this is expanded to here, 3 minutes it's here, 7 minutes it's here, and by 17 minutes do you see the entire bubble is loaded with whatever that stuff is. Now what is that stuff? It was carriage, and Brian is the guy that gets to go out. You get a free dinner tonight, Brian, if you want to join Jim.
Dinner's on Pagani.
Oh, Pagani. All right. At any rate, yeah. What is happening is that we have a chip right here that's capable of sitting on a desktop, holding gas in it virtually forever. And yet when you put water on that, the water is imbibed, and as it's imbibed, it's driving out the natural gas from the pore space. And the speed with which this gas can be driven out is just absolutely amazing. Now, let me just finish up right here. Here's a surface view of the same thing, and you can sure see in this particular slide the gas bubbles coming out. It's very, very clear. Now, one last point. I always go over the length of time allotted. One last point is this. When a gas well is drilled, there's a period of induced imbibition, and that induced imbibition occurs right here. Now, induced imbibition means that the pressure of the frac fluid against the wall of the fracture is a lot higher than any fluid pressure within the fracture, so that what you have is a space that has a water saturation of 100%, and rock of shale, particularly of water saturation 100%, does not produce gas very well. The operators are letting the well sit for a period of time, and this allows the well to mature to the point that it can then produce a lot of gas. This is a period in which natural imbibition occurs, and natural imbibition is a consequence of let me go through this. Natural imbibition is a consequence of the fact that capillary entry pressure for a high water saturation, this scale right here horizontally is a water saturation, this is the capillary entry pressure. So rock next to a fracture has a fairly low capillary entry pressure. Back in the Marcellus Shale itself, where it might have a water saturation between 10 and 20%, capillary entry pressure is a lot higher. So we have a situation that is not in equilibrium. And what has to happen is that the operators then let this well sit so that this state of non-equilibrium between the two capillary pressures can come to equilibrium. And basically what happens is this is a period of time in which the water that basically blocks flow of gas out of the well can re-equilibrate, basically opening up channels so that gas can escape. Now, what we find then is that the zone of induced imbibition is about this wide right in here like this. These, incidentally, are natural hydraulic fractures, the way that you would look at them in rock. And another knock I have on National Geographic is look at how they drew their fractures compared with the real world, so that someone didn't do their homework. And you know, the view that the public has now is a cartoon that just has nothing to do with reality. But that's a story for another day. So here is the zone of induced imbibition, and I've drawn this about to scale right now. These cliffs at Taganic Falls, this is the Geneseo gas shale, are 300 feet tall, about the size of induced hydraulic fractures. This is the zone of imbibition right in here, where water saturation is 100%. And the reason that wells are given a chance to cure is that the water that's captured next to one of these fractures then has time to filter out sideways, decrease the water saturation so gas can flow out of the well. And this basically is a cartoon of the same thing. Now, one last point, and then I'll quit, which is this. Gas shales consist of two components. One is a water-wet matrix, and the other is an interconnected network of oil-wet organic matter, which is shown right in here like this. And the only reason that gas shale produces as effectively as it does is that the water saturation of the rock, when it is less than about 30%, then allows for gas to make its way through this network of oil-wet kerogen matrix out to the hydraulic fracture. If the kerogen was not interconnected, as shown right in here, then gas shale would not work as an economic reservoir. Some of the gas shales of the world don't produce very well, and I suspect that probably the first reason for that is that the interconnectivity of this oil-wet kerogen is not quite as good, and therefore there's less of a chance for gas to make its way out of the matrix. Okay, I'll end with that thought and continue a discussion with us right here.